Four dogs can chase each other forever around the same square and still crash into the center after exactly one side length of running. Put one dog at each corner. Each dog runs at the same speed, always aiming directly at the dog ahead. No dog ever reaches its target early. Instead, the whole square twists, shrinks, and draws four perfect spirals. Then all four dogs meet at one point. Here's the part I want you to predict. As the dogs curl inward, how many complete laps does each one make before the collision? 1, 5, some large but finite number? It's infinitely many. That sounds incompatible with arriving in a finite time, and honestly, that was my first objection. Infinite turns should require infinite running. Except the final turns become absurdly small, and they become small quickly enough that their total length stays finite. But that only moves the mystery. Why does the shape stay a square? Why is the path a genuine mathematical spiral rather than merely something spiral-ish? And how can we know the exact collision time without laboriously tracing every curl? Watch one dog for a moment. Its target is moving sideways while the dog approaches it, so the dog's direction must keep rotating. Now watch all four together. Every dog makes precisely the same mistake, rotated by 90 degrees. That symmetry is doing almost everything. We just need to catch it in the act. The square survives because no corner gets special treatment. Rotate the entire situation by 90 degrees and dog 1 lands where dog 2 was, dog 2 lands where dog 3 was, and every velocity arrow lands on another velocity arrow. A moment later, the same rotational symmetry must still be there, so the dogs can't suddenly form a rectangle. Which direction would be the long direction? The rules haven't chosen one. They can't form a lopsided quadrilateral either, because rotating that shape would have to leave it unchanged. The only possibility is another square, smaller and turned slightly from the first. This gives us a much cleaner object to follow. Forget four separate animals for a second. Draw the square connecting them. As time passes, that square contracts and rotates its one rigid pattern, although it isn't a rigid object. Every side gets shorter at the same rate. Every corner advances through the same angle. Now pause on one corner. The dog there aims along one side of the square, toward the next corner. But relative to the center, that direction is exactly halfway between two jobs, moving inward and moving around. 45 degrees inward, 45 degrees sideways. That's the precise turn in the mechanism. The dog isn't choosing a spiral. It only follows a straight line toward its neighbor at each instant. Symmetry keeps rotating that straight line underneath it, permanently splitting the dog's speed into an inward part and a sideways part, equal parts in fact. And once those two components are visible, the collision time falls out almost suspiciously fast. That equal inward component means every dog approaches the center at speed, v divided by the square root of 2, constant speed, not approximately constant. The radial distance drops along a straight line graph, called the starting center, to corner distance r0. Then the collision time is r0 divided by v over root 2, which is root 2 times r0 over v. That expression looks detached from the square, so use its diagonal. A square with side length s has center to corner distance s over root 2. Substitute that, and everything cancels. The collision time is s over v. So if each dog runs at 1 meter per second around a square with 10 meter sides, they meet after 10 seconds. Each dog runs for 10 seconds at 1 meter per second, meaning its curved path is exactly 10 meters long, the length of one original side. I didn't expect that. The target keeps fleeing sideways. The dog's path winds around infinitely often, and yet the total chase is no longer than the direct run from one starting corner to the next. The curve spends its length very efficiently because the sideways motion continually shrinks with the radius. There's another way to see the side length collapse directly. Look only at two neighboring dogs and the distance between them. The first dog runs along their connecting side at full speed. The second dog's velocity is perpendicular to that same side, so at that instant it contributes nothing to their separation. Their distance therefore decreases at speed v. Starting from s, it hits 0 after s over v. Nice. But this argument tells us when they meet, not what curve they draw. For that, the equal inward and sideways speeds have one more consequence. The sideways speed is also v over root 2, but sideways speed isn't angular speed. Running sideways around a large circle produces a modest change in angle. The same motion near the center whips through a much larger angle. Specifically, angular speed is sideways speed divided by radius. So while the radius falls at a constant rate, the turning rate grows like 1 over the radius. Closer means faster turning. Half the radius, twice the angular speed. 1/10 the radius, 10 times the angular speed. Now compare a tiny inward change with the angle gained during it. Dividing the angular change by the radial change gives -1 over r. Integrate that relationship and the angle becomes the logarithm of the starting radius divided by the current radius. Or, solving for the radius, r equals r0 times e to the minus theta. That is a logarithmic spiral. The equation matters because it gives the curve a remarkable repeating structure. After one complete turn, theta increases by 2 pi, so the radius is multiplied by e to the minus 2 pi about 0.87. Each full coil is only about 1/535th the size of the previous one. That is vicious shrinkage. After just 2 turns, the radius is roughly 3.5 millionths of where it began. The animation hasn't stopped spiraling. The later coils have simply become far smaller than a pixel, and this is why the curve looks almost as if it dives straight into the center after the first loop. It doesn't. Magnify the endpoint, and there's another copy of the same winding behavior. Magnify again, same story. So where, exactly, are those infinitely many turns hiding in the finite chase? The turns are hiding in the last slivers of time. Let tau be the time remaining before the collision. Because radius decreases at a constant rate, the radius is proportional to tau. Put that into the spiral equation, and the angle is essentially minus the logarithm of tau. As tau approaches 0, that logarithm grows without bound. There is no final turn. For any lap you name, however ridiculous, the dog completes it before the collision, but completing one more lap requires shrinking the radius by that same factor of e to the minus 2 pi. Since remaining time is proportional to radius, the remaining time also gets divided by about 5/35 after every turn. Suppose the first full revolution leaves 1 second on the clock. The next needs almost all of that second, but after it, there are only about 1 times 9 milliseconds left. After another, roughly 3.5 microseconds, then nanoseconds. The laps don't take equal chunks of time. They pile up geometrically at the collision instant. This is the same basic trick behind walking half the remaining distance then half again, forever. Infinite stages can have a finite total. But the dogs make it more dramatic. Instead of merely crossing smaller intervals, their direction rotates without limit. At the exact center, the heading never settles to a final angle. That last point is a real caveat, not a paradox. The pursuit rule says to aim at the next dog. At the collision, all dogs occupy the same point, so toward the next dog no longer defines a direction. The mathematical motion ends there. Asking which way they face afterward is asking the rule to operate where it has stopped making sense. Still, this perfect pileup depends on 4 dogs starting perfectly. Disturb one corner, and symmetry can't protect the square. Does the collision survive? With one dog displaced, the shape immediately stops being a square. Side lengths differ. The velocity directions no longer match under quarter turns, and our neat inward versus sideways split disappears. So the 4 original logarithmic spirals are not preserved. That perfection was earned by symmetry. Do the dogs still all collide? Sometimes they bunch together very closely. Sometimes one dog catches its target first, and then the original 4-way rule needs a decision about what happens next. There isn't one universal answer hiding behind the symmetric calculation. The starting arrangement matters. There's also a subtler way to spoil the spiral while keeping the initial square. Update the directions only occasionally. Real dogs can't continuously recompute an exact bearing. If they choose a target direction, run straight for half a second, then aim again, their paths become polygons. Use smaller and smaller time steps, and those polygonal paths converge toward the smooth pursuit curves. This is worth seeing because a careless simulation can create the wrong ending. With large steps, a dog may overshoot its target, the square may jitter, or the markers may orbit a tiny hole forever. None of that disproves the collision. It means the numerical update is too coarse near the center, exactly where angular speed is exploding. Try steps of 1 second, then a tenth, then 100th. The corners in each trail multiply. The apparent central hole contracts. The collision time approaches s over v, and the path length approaches s. So we found what has to be ideal, equal speeds, a perfect square, and continuously updated directions. But 4 isn't sacred. Put dogs on a triangle, a pentagon, or a 50-sided polygon, and the same symmetry returns, with a different spiral hiding inside it. For any regular polygon, rotational symmetry again forces the formation to remain regular while it shrinks and turns. The only change is the angle between a dog's direction and its inward radius. With n dogs, that inward component is v times sine of pi over n. The sideways component is v times cosine of pi over n. Divide one by the other, and the spiral becomes r equals r0 times e to the minus theta times tangent of pi over n. For 3 dogs, the radius drops relatively quickly and the curve turns gently. For 4, tangent of pi over 4 is 1, giving our original e to the minus theta. Add more dogs and the inward component gets smaller. Each dog mostly runs sideways, so the pack wins around many more times before reaching the center. The meeting time also changes. In terms of the original side length s, it is s divided by 2v sine squared of pi over n. 4 dogs give s over v. 6 dogs take 2s over v with many dogs. The time grows roughly like n squared. Picture 50 dogs around an enormous regular polygon. Each one aims at a neighbor only a small angle inward from sideways. They're definitely approaching the center, but grudgingly. The polygon rotates again and again, tightening into something that looks almost circular, and now the opening animation means something different. Those 4 dogs weren't tracing spirals because a spiral was programmed into them. Nobody knew where the center was. Nobody steered inward. Each dog used only one local instruction: look at the next dog and run. The center, the shrinking square, the logarithm, the infinite turning, and the exact one-side length journey all emerged from 4 identical wrong pursuits fitting together perfectly. Each target escapes forever. The formation doesn't.